Thank you. Okay, so as before, I think most of you have them, but there are lecture notes up here on paper. It's really handy to have as we go through. And again, this is the website you go to, and copies of the lecture notes are there, as are I've been asked to give you homework assignments, so don't blame me, but there are homework assignments up there too. And there's a new one every day. Okay, so what I wanted to talk about today. So yesterday, what did we do yesterday? So yesterday we really started from the fundamentals. So we said, okay, just started with talking about like what an orthobasis was, and we really just viewed that as being something which we can use to sort of discretize a space, like translate a regular signal into a list of numbers. And then, we the second lecture, we started to get it, okay, now that we have this idea of an orthobasis in place, we kind of introduced this notion of sparsity, right? And that was the idea where we kind of have a model for a signal or interest, a signal or image of interest, where the model is, not that it lies in some subspace, but rather that it can be written as a superposition of a small number of terms from a fixed basis. And then we saw how sort of examples of how models like this arise and just kind of things were interesting. So really the classical example is looking at images in a wavelet domain. And so that's really a good canonical version of what we mean by sparsity. Okay, so then in the last hour yesterday, we looked at this problem of, say, okay, if I want to approximate a signal or image by sort of a sparse superposition of a fixed vectors, if I were to do that approximation in an orthobasis, it's a trivial problem to solve. I just take the elements that have the biggest expansion coefficients. If I have an overcomplete dictionary, right? So in some sense, I'm trying to solve an underdetermined problem. We looked at a couple algorithms for doing that. So we had these two matching pursuit algorithms. This matching pursuit and orthogonal matching pursuit, which kind of iteratively went through selecting out different columns. And then we looked at basis pursuit, right? And basis pursuit was sort of rewrote the program as an optimization program. And then, just tried to solve it sort of more holistically, right? And then we just had proved a little result at the very end, showing that basis, any solution to basis pursuit, it was parsimonious in that, like, it wouldn't use more than n terms. So if I had a length n, so if I had a vector, a signal f, I'll say it, which is in Rn, and I wanted to write it as a sparse superposition of terms from alpha, where this was p by n, if I sort of selected this by solving beta equals f. If I solve this program, no matter what f is, like our argument had nothing to do with that. No matter what f is, the solution to this program won't use more than n terms. So in some sense, it's efficient. Okay, so what we want to sort of get at today now is this, start to get at this idea of sparse recovery using L1. And so what I wanted to do, first of all, was talk about in depth for the first hour a little bit about this idea of sparse decomposition. I'm going to give a particular example of when we can expect, what do we need out of this matrix and out of the sparsity to make sure that we have a unique sparse decomposition that exists. And there's a language you can couch this problem in, and it's kind of the language of uncertainty principles. Right? So what we'll see today is we'll talk about a particular case, in this first hour, a very particular case for this dictionary phi, and it will be this union of two n by n systems. So this is n by n, and this is n by n, so this is going to be all 2n by n, and this will be spikes, and this will be signs. So this will be an identity matrix, and this will be a Fourier matrix. right? And then all I want to do, just to kind of give you an appreciation of say this idea of sparse approximation, say, okay, if I have an overcomplete dictionary which looks like this, what can I say about sparse solutions to this system of equations being unique? Okay, so that's what I want to do for the first hour. Okay, so let's just get right to it. Okay, so here's here's this dictionary. So we're going to focus for this again this first hour just on this one problem, and just to be clear, like if we sort of draw a schematic of what this system looks like. Again, it's n by 2n, so it's an underdetermined system, and the kind of the key thing to recognize is that these two halves of the matrix, they're completely different from one another. Right, of course, this half is just the identity matrix, so it's what I call a spike basis. It's basically, sort of just a standard basis in Rn. So if I'm sort of sparse in the spike basis, what does that mean? It means my signal just has a few blips in it. And then the other sort of basis I have next to it is a sinusoidal basis. So this, when we zoom out like this looks kind of weird, but if you just look at like one row of this, in this case it looks like a cosine. Right, and of course, this matrix is complex in general. So this is just the real part of it, but that won't cause too many complications. Okay, so what's kind of special about this pair, right? Which allows us to really say a lot about say sparse solutions to this system of equations, is these two things are like maximally different from one another. Right, and so we can, there's many ways we can talk about things being maximally different from one another. But like one thing we could say is like, if I have one element from this basis, a spike, it takes n sinusoids to build up a spike, right? And it also takes the n spikes to build up a complex sinusoid, right? So in some sense, there's each basis takes all of the other basis functions to represent them. Right? So that's one way we can talk about these two things being maximally different. Okay, so like why am I sort of interested in this? So what we can think of now, we're thinking about sort of signals that maybe have sparse representations in this dictionary. Like what are those signals look like? Well, they look like, basically signals that have two completely different types of phenomena in them, right? Maybe they have a couple signs in them and a couple spikes in them. Right? So these two completely different things. So then the question is, okay, if I give you a superposition of spikes and signs, right? If I find a sparse solution to this system of equations, what that's basically saying is like, when can I really untangle, okay, if I gave you a length 1,000 signal, there's 5 spikes and 5 signs, when can I say, okay, this is, the sort of unique sparse way to write this signal. Okay, so that's what we're interested in. Okay, so now let's just consider this one case, just to make, kind of our goals a little bit clear. So let's just say the signal I give you is a sinusoid, right? It's just a sinusoid that's harmonic. And I say, well, I want you to write f using this dictionary. Well, there are many ways you could do that, right? There is, say, a very natural way you could do it, and that I just put, say, a 1 in the right location in the second half of the vector. So let me just be clear here. So I can sort of, just like I divide this dictionary into two parts, I can sort of divide the representation into two parts too. I call this alpha 1 and alpha 2. So in some sense, these are telling me at what locations to put the spikes, and this half would be telling me at what frequencies to put the sinusoids. Okay, so if f, if this left-hand side f, if this is just the sinusoid, there's again, since this is an underdetermined system, it has a huge null space, it has a null space of dimension n. If I give you any vector f, there's of course an infinite number of ways I can write that f with this right-hand side. But if f is like a sinusoid, there's kind of one, what I would call natural way you would write it. And that's as simply just picking off, the correct column out of the second ortho basis, right? And so, if this is your signal f, kind of what you might say the most natural way to say is, okay, what this alpha really should be is all zeros, a 1 here, and then all zeros after that. Okay, so, we might ask, like, how do we find such a representation? So let's just start to answer that question by looking how we might not find a representation like that. So one thing we could say is, okay, if I give you any signal, right, what I might ask for is, okay, I know there are an infinite number of ways to write that signal. Why don't you just give me the one that has the smallest amount of energy? Right, and so what are you doing when you say that? I mean, again, because all the rows of I are orthogonal to one another, and all the rows of F are orthogonal to one another, since these are both orthotransforms, all the rows of this matrix are orthogonal to one another. So if I ask for if I give you a signal F and say I ask for the coefficient sequence which has quote unquote minimal energy, what I'm sort of doing is I'm just projecting this vector. What I'm doing is I'm finding this vector in R2n, which is in the row space of this matrix, right? And so since these are both orthogonal to one another, if I look at phi star, right, that's going to be a n by n matrix, and it's just a scale times the identity. Okay. So in some sense, what I'm doing when I rewrite F like this, and so that all this is again just a reproducing formula for F, is I'm saying, okay, look, what I'm using as sort of the expansion coefficients for F is 1/2 phi star times F. So if we do that with a sinusoid, what does it look like? Well, I mean, it looks like this. It looks something like much less natural, right? So if I correlate all the entries with a sinusoid, what do I get? In the first half, I get a sinusoidal vector. In the second half, I just get a point, right? So in some sense, this answer here is the minimal energy solution to the system of equations. And in some sense, it's not very satisfying, in that it's sort of making this signal, which should be just exactly one element in this dictionary, making it much more complicated than it should be. Okay, so that's maybe not what we want. We can make sort of things even more pronounced. So let's say we have F, and it's when we look at this, like, why are we getting this sinusoid up here? Well, if I have a sinusoid, again, I correlate it with the spike. Like, what do I get? I get a sample of that sinusoid, right? So all this is just the identity applied to your signal. So I just get a sinusoid here, and then I get a Fourier transform of the sinusoid on the bottom part of it, right? And so this, gives me a sinusoid plus a spike, which isn't as nice as just giving me the single spike at the frequency that I like. But it becomes even worse if, say, I have just a couple spikes and a couple sines. So here I have F is almost the same thing. It's still a very simple signal, but now it's a sum of spikes at two locations. You can probably guess where those locations are, here and here. And then it's a sum of sinusoids at two different frequencies, right? So now, when I take this signal and correlate it with every column of the dictionary, you get a mess. Right? You get stuff that's non-zero everywhere. Right? So even though I know that there's a sort of very parsimonious way I could represent this signal using columns from this matrix, so it's basically a superposition of 4 columns, 2 spikes and 2 sines. Just simply finding the least squares or the minimum energy solution doesn't do it. It gives me kind of a wreck, something which is not sparse at all. Okay. So, in some sense, as I've stated here, really the problem is that this minimum energy decomposition, it mixes together the spikes and the sines, right? Since you're, whatever spikes and sines you have, you're correlating, all this, when you have a superposition of spikes and sines here, when I correlate the spikes against this basis, I get something very sparse. When I correlate the sinusoidal components against this basis, I get something completely global. And then the exact opposite is true when I correlate against the members of this part of the dictionary. The sinusoidal components will be very sparse when I correlate them, but the spike components will be spread out kind of all over. Okay. So, what we want to do is we want to say, okay, instead of just doing this sort of minimal energy projection, what I'd like to do is say, look, let's say, I know that F is a superposition of some small number of spikes and some small number of sinusoids. The first question I could ask is, what is the point at which this sort of sparse solution becomes non-unique? And what I mean by that is, like, let's say tell you that F is a sum of 2 spikes and 2 sines. And then you can ask, is there any sparser way I could write F? Is there any way that F could be more simpler than 2 spikes and 2 sines? Right? And that answer happens to be no. But then it's like, okay, well, what if I have n spikes and n sines? Right? Then clearly the problem, becomes undetermined. If I have n over 2 spikes and n over 2 sines, is there a simpler way to do it? Well, there's many ways I can write F probably as the superposition of n components. Right? So there's some breaking point where if I ask, is the kind of sparse solution to this system of equations unique in the sense that there is no solution which is sparser, there's just kind of a break point at which that starts to fall apart. So what we really want to do, and again, where we're going to be focused on this very specialized case in this lecture, is just figure out what that breaking point is for this particular case. Right, and it's actually, the point of this is, well, first of all, we learn a lot about this, unions of spikes and sines, but really what it does is it really draws out what's important in the more general problem. Like, what do we need for sparse decompositions to be well defined? Okay, and so what we'll say is, like, if I want to sort of be able to clearly separate this into like 2 spikes and 2 sines. Like what this kind of depends on is just sort of a new type of what you might call uncertainty principle between the discrete time and the discrete frequency domains. Okay, so and basically what it says is, it's sort of a very different nature than maybe the uncertainty principles you're used to from quantum mechanics, right? And so, what this is really about is, when you think about the Heisenberg uncertainty principle in quantum mechanics, what that says is, okay, if I have some signal in time and some signal in frequency, those two things can't be, in some sense, concentrated too greatly at the same time. And there's a very technical definition of concentration. It's basically the second moment. If I look at the product of the second moment of two things, it's bounded below by something. Okay, so but here, what we're going to do is we're going to have kind of a very different notion of what we mean by uncertainty principle. And essentially what it's going to say is, you can't have anything which is sort of simultaneously sparse in the time domain and sparse in the frequency domain, right? And so let's just look at exactly what we mean by that. Okay, so these are sort of ideas that were kind of first laid down in the late 80s by David Donahoe and his collaborator Stark. Now, looking back on that stuff, after we've had sort of a lot of experience with sparse solutions to underdetermined system of equations, we can actually get at the results that are in that paper in a far easier way than they did in 1989. And that's kind of going to be the content of what's left here. So, the proofs that I'll give you are sort of much more straightforward in some sense. Okay, so here's what this uncertainty principle says. So we're going to state, just a fact about the discrete Fourier transform and the identity basis. We're going to prove that fact, and then we're going to talk about its implications for its sparsest decomposition. All right, so here's a fact. And basically what this says is, again, if I have a signal, it can't be too sparse in both time and frequency simultaneously. So let's let F just be a vector in Cn, and let F hat be its discrete Fourier transform, right? And so then, what I'm going to call the size of the support in time. So T is the support of the F in time. So basically T is just a set of indices where F is non-zero. And then omega is the support of F in frequency domain. So basically omega is the locations of the Fourier transform that are non-zero. Okay, so here's what we can show. Our uncertainty principle takes the following form, right? What we can say is the product of the number of non-zero terms in time and the number of non-zero frequencies is lower bounded by n. right? And then what that immediately implies is that the sum of the number of non-zero terms in time plus the non-zero terms in frequency, that's lower bounded by 2 times the square root of n. So this thing on top immediately implies this thing on bottom, and that's just because, like, if I have t times omega bigger than n, so that means square root of t times omega is bigger than square root of n. And then I just have this fact that arithmetic mean always dominates geometric mean. Right? So this is less than or equal to the sum of these two things divided by 2. That's just always true. So then, combining this and this gives you this second equation here. Okay, so this is what we mean by discrete time uncertainty principle. It's a statement about the time domain and the frequency domain. And rather than talking about like second moments, defining concentration in terms of second moments, it's defining concentration in terms of number of terms that are strictly non-zero. Okay, so this is what we want to prove. That no matter what signal you give me, right, there is no way that when I look at the number of non-zero terms it has in time and the non-zero terms it has in frequency, and I multiply those two, there's no way it can be smaller than n. Right? And in fact, we'll prove that this is in some sense tight, that we can construct signals for which this is exactly true. We'll see that at the end. Okay. So here's the reason why this works. And again, this was sort of all laid out in the late 80s, but if you go back and look at that paper, it's not that it's a mess, it's just the way things are written are sort of very different than how we understand them now. So this is in some sense a more direct way to think about it. Okay, so how we're going to do this, right? And again, this gets at a lot of what's important in sparse recovery, is we're going to talk about this uncertainty principle in the context of looking at this sort of matrix psi, which contains both of these orthobases together, and we're going to again develop this uncertainty principle in the by looking at the sort of structure of the singular values of submatrices of appropriate size of this matrix psi. Okay, so this is what we do. So just remember that this T is the support of F in time. Right? And omega is the support of F hat in frequency. Okay, so now this is what we define. So this is then we define this matrix psi t omega, and what this is a n by size of t plus size of omega matrix, and how we form it is we take this and we take the columns corresponding to T from this part of the matrix, and we take the columns corresponding to omega to this part of the matrix, and then we just put them into another matrix called psi t omega. Okay, so this is again has n columns, and it has t plus omega, n rows and t plus omega columns. Okay, so now kind of the important thing to realize, right, is that for if we have a particular signal, f, and what we can say is that if f is supported on t in the time domain, and it's supported on omega in the frequency domain, right, then it has to be true. So first of all, it's always true. So since if I look at identity Fourier, and then I look at some whatever signal f here, and then I put minus its Fourier transform here, right? If I look at this is f, minus f hat, and then this is going to be 0, right? So whatever, the vectors kind of in the null space of this matrix, they consist of Fourier transform pairs. So the top half of the vector, or the bottom half of the vector, is negative the Fourier transform of the top half of the vector. That's exactly like how you characterize things in the null space of this matrix. So like if I'm supported on, if I have a signal f which is supported on t in the time domain and supported on omega in the frequency domain, and then if I just sort of throw away all the 0 terms, right, then F restricted to T and F hat restricted to omega, these should also be in the null space of this other matrix. So all I've done is throw away all the terms which are 0. Okay, so, so what we can say then, what we're kind of looking at here, is we could say that, okay, look, if we can't find any vectors in the null space of phi t omega, right? So phi t omega does not have a null space, then that means it's impossible to find an f that's supported on t in the time domain and omega in the frequency domain. Right, so that's kind of what we're after. That's what it means for t and omega that don't allow sort of an f that's concentrated on a certain set of time and omega at another certain set of frequencies. So it's just an equivalent statement. So we can sort of examine when this is true simply by asking the question, if I take a certain subset of columns from this dictionary, a certain subset of columns from this half of the dictionary, put them into a smaller matrix, and say, is this matrix rank deficient? Right? Does this matrix have a null space? If not, then it's impossible to find a signal that has this support t and this other support t in time and support omega in frequency. It's just impossible. Really, it's almost by definition. Okay, so that's what we're going to do. We're going to come up, what we do is we just come up now with conditions on the size of t and omega such that this submatrix psi t omega does not have a null space. Okay, so that's what we do. And one way we can see if it has a null space is, another way to talk about it is and when I take its transpose with itself, so this is a t plus omega by t plus omega matrix, and we just got to just ask, is this matrix invertible? Okay, so let's see when this matrix is invertible. What can we say about it? Okay, so now, again, just to sort of make things clear. Okay, so what this sort of IT is, again, so IT, what I do is I just kind of pull out right, so this would be like if t was 1, 3, 5. I just pull out the appropriate columns of the identity matrix. So the I always has, it has exactly t columns, and each column has exactly 1, 1 in it. Right, and then f omega, this is, going to be sinusoids, but they're going to be sinusoids at the frequencies that I pull out, right? So this is, say, these are the sinusoids with frequencies in omega. Right, and so what do we know about f omega? It means, again, it's an n by size of omega matrix, and every entry in this matrix has the same size. It has a size equal to 1 over the square root of n, right? And so all entries have magnitude 1 over the square root of n. Right, and that's just from the way I've defined that. So if we just go back to this page here, that's just what this looks like. So of course this e part always has magnitude 1. So all the entries in this have magnitude 1 over square root of n. Okay, so what do? I just simply, if I look at this matrix, this is what it looks like. So it looks, it looks like this guy transposed times this guy. That's just an identity matrix, right? That's what I get in the upper left-hand corner. That's the identity. Likewise, if I take, since the columns here are orthogonal, if I take f omega star f omega, that also gives me the identity. That's down here. Right, and then if I take this guy and take the transpose of this times f, so it star f omega, Basically, this just subsamples the rows of F omega. Right? So this is basically a T by omega matrix, which essentially what I've done, what this matrix is it's basically I take a Fourier matrix, I take the columns of that Fourier matrix corresponding to omega, I take the rows of that Fourier matrix corresponding to T. That's exactly what what is in these kind of what's in this upper right-hand corner, and its transpose is just what's in the lower left-hand corner. Okay, so again, since this is just sort of subsampling the rows of this matrix, everything in this matrix M, I'll call it here, again has the same size. It has magnitude 1 over square root of M. Okay, so this kind of product of psi t gamma star psi t gamma, I can rewrite this as the identity plus this matrix G, where G has these two off-diagonal matrices, M and M star. And again, the important thing about M and M star is they all have a magnitude exactly equal to 1. Okay, so what we have here is, since this is true, and what I want to ask now is, when is this matrix phi t gamma star phi t gamma, when is it invertible? Right? Since it's symmetric and at least positive semi-definite, right? This matrix being invertible is the same as all its eigenvalues being positive, right? And since I can write this as I plus G, right? I know that the operator norm of I is equal to 1. I know that this eigenvalues will be positive if all the eigenvalues of G are less than or equal to 1. Right, and so one way I could talk about all the eigenvalues of G being less than or equal to 1, if I talk about the operator norm of G being less than or equal to 1. Right, so the maximum eigenvalue of G is less than 1. That guarantees that there are all the eigenvalues of phi star t gamma, phi psi t gamma, guarantees all these eigenvalues are positive, which guarantees this is invertible, which then guarantees that there's no null space of phi t gamma, which says there's nothing I can find, there's no way I can find a signal that's supported on t in time and omega in frequency such that phi t gamma is equal to 0, which just means there's no signal supported on t in time and omega in frequency, period. So it all kind of loops back to that. Okay, so we've boiled down this whole problem into showing that, the operator norm of this G, another way to say it is all the eigenvalues of this G are less than 1. Okay, so we can actually do this with basically a very simple calculation. So let's just look at G star G, right? So what I can say is, okay, if I want to look at the operator norm of G, that's the same as kind of the square root of the operator norm of this matrix, G star G. So when I take G star G, what do I get? I get MM star up here and M star M down here. Basically, since this matrix is block diagonal, its largest eigenvalue will be the maximum of the largest eigenvalues of these two matrices. These two matrices happen, since they're just one's MM star, one's M star M, these two matrices have the same largest eigenvalue. So all we're saying now is that the operator norm of G squared, which is equal to the operator norm of G star G, is also just going to be equal to the operator norm of M star M. Okay, so the reason that we're doing all this is we can actually very quickly put a bound on what the operator norm of M star M is. Okay, so again, all we need to do now is so what basically this manipulation says, it says if the largest eigenvalue of M star M is less than 1, that necessarily means the largest eigenvalue of G is less than 1, which means, if we, again, back up our ways through this, it means there's no signal I can find that's supported on t in time and omega in the frequency domain. Okay, so how do we get a bound on this? You can actually do something very crude, but it turns out to be tight, and that, again, we'll be able to find a signal that meets these conditions at the end. So here's what you could say. You could say, okay, the operator norm of m star m. So again, this is just equal to the trace of m star m, right? So basically, what you're saying is, in this case, you're saying just the general fact is, so this is a symmetric, at least positive semi-definite matrix. So its largest eigenvalue is less than or equal to the sum of the squares of the square root of the sum of the squares of all of its eigenvalues, right? So it's kind of like the infinity norm is less than the L2 norm. Okay, so we always have this, that the operator norm is less than this trace. So, but this is actually easy to compute, right? So if I just to add up, what just calculate what is along the diagonal of this matrix M star M, right? It's easy to do, right? All this is again this matrix M. It just looks like this, right? It's basically each row of M is each column of M is a complex sinusoid which has been subsampled at a sort of subsampled at these times t. Okay, so what does that mean? It means when I actually compute what's along the diagonal of this, this is what it is. It's like one of these samples at frequency omega, just multiplied by its complex conjugate. Right? So when I multiply these things up and sum over t, what do I get? I just get the size of t over m. Right? So this m star m, what it has along its diagonal is really just this size of is really just the same thing. It's just the number of elements in t divided by n. Right? So then when I look at its trace, since m star m is cap size of omega by size of omega, the trace, the sum of all these terms, they're all the same thing, are just the size of omega times the size of t divided by n. Okay, so then that gives it to us. Basically, we say, okay, if this is less than 1, right, which basically means that the product of these two things is less than n, that means that this operator norm of g is less than 1. That means that this psi t omega doesn't have a null space, and that in turn means it's impossible to find an f that's supported on t such that its Fourier transform has something supported on omega. Right, so that's really all you have to do. So it's a sort of a very straightforward argument, and it gives you an immediate bound on saying like, look, no matter what discrete vector you give me, if I count the number of non-zero terms it has in time and the number of non-zero terms in frequency, those two things have to obey a relationship, and that relationship is they have to be bigger than n, basically. Okay. So that's good. So it's also sort of interesting about this is there are sort of locations in this argument where things are kind of crude. Actually, there's exactly one place where we kind of use a very harsh bound. So everything in this argument is pretty tight, except for this statement right here, right? This fact that I have the operator norm and I bound it by the trace. Right, so I'm basically saying that the largest eigenvalue is less than, in this case, the sum of its eigenvalues. Okay, and so this is sort of the one place we're being very crude. Otherwise, everything else is a quality, or if and only if. So this is the only kind of non-reversible step in the entire proof, and it is a crude one. But then you can definitely find signals, though, that meet this relationship with equality. Right? And here's an example of one such signal. There are actually many, but here's the easiest one to understand. So what I do is I have something called the Dirac cone. Right? And so what I do is it requires n to be a perfect square. So let's say n is 256. And then what I do is I take square root of n spikes of height 1, and I space them square root of n apart. Right, so now I have 8, so if I have n is equal to 256, I have 8 spikes spaced 8 apart. Okay, so it just so happens a signal like this has a Fourier transform which looks exactly the same. Right, and so let's see, one way you can think about this is, if you'll recall that sort of things that are zero pad like this. So anytime I have a signal which has a non-zero component, and then, in this case, 7 zeros, and then another non-zero component, and then 7 zeros, etc. So you have anytime you, it's like, if this is like kind of like the output from something which is upsampling by a factor of 8. Right? So you know in the Fourier domain, signals like that, they have to be periodic. I'm going to get whatever I'm going to get something here, and then that's just going to be copied 7 more times. All right, so anything that has a structure, non-zero terms, 7 zero terms, not one non-zero term, 7 zero terms, has this kind of periodic structure in the Fourier domain. All right, and not only that, this first period, what it's determined by kind of the 8-point DFT of these, 8 non-zero terms. All right, and since this is flat, when I take the 8-point DFT, it maps to a spike and then 0, 0, 0. All right, so the periodicity is given to you just from the fact that this is non-zero and then a bunch of zeros, and then what this first period looks like is just the DFT of these spikes. So that's just kind of like basic signal processing in Fourier terms. That's just why one of these maps to the other. But at the end of the day, what the point is like here, look, this has square root of n non-zero terms of time. This has square root of n non-zero terms of frequency. The product of those two things is obviously equal to n. So we found a signal which matches this lower bound with the quality. Okay. So that's good. So, excuse me. All right, so that's what we mean by this discrete time uncertainty principle. It means we can't find any signal. Right? There's no such signal that has a support in time and a support in frequency. When I add up those two sets of non-zero terms, it can't be bigger than it can't be smaller than 2 times the square root of that. Okay. So then that's great, and that's sort of maybe of intellectual interest, independent intellectual interest. But what's also great is it has sort of an immediate impact on our kind of sparseness decomposition problem. Right? When we have this sort of question about, I have a sort of a simple way to explain this signal, and that I can write it as, it's a sum of 3 spikes and 4 signs, right? Is there a sparser way I can write that signal? Right? And then we'll say that, if there is a way to write that signal using a total number of spikes and signs that's less than 2 times the square root of n, less than the square root of n, then no, there's no other way you can write it more sparsely. And again, it's just taking this uncertainty principle and reworking it. Okay, so that's what we do next. So we figured out what this, or talked about what this uncertainty principle is. We proved it from top to bottom. And now let's talk about its implications for finding this sparse decomposition. Okay, so now what I say is f really is, let's just take f of t to really be a superposition of a small number of spikes and a small number of sinusoids. And so now, what I'm going to say is, we have, just let me rewrite this because it'll be good to have here later on. I times alpha, and this is I times f times alpha 1, alpha 2, right? And let's say, we have let's say I give you an f that uses, say, less than square root of n spikes and signs. All right, and then I just ask you the question. Is there a sparser way you could write f in this dictionary? Is there a sparser decomposition for f? Right, and at some point there is, because if I gave you an f that had like say n spikes in it, and or let's say n over 2 spikes and n over 2 signs, you say, is there a way as sparse I could write f? And yeah, there are many ways. Right, there are many ways I can pick n over 2 spikes and n over 2 signs to build up any signal at all. Right, so the idea is that if there is kind of a sparse representation for f, or sparse, here I mean very sparse, so again using less, not less than n, but less than square root of n terms, then in some sense that sparse decomposition is unique. Unique in the sense that there's nothing that's as sparse or sparser that will give you the same signal. Okay. So that's what we want to argue. So I say if I give you an f, and I've composed f using fewer than square root of n, total spikes plus signs. And then I ask, is there another way to write f using the same number or fewer terms? The answer to this is no. Okay, and it's actually pretty easy to see why not. So the way we say is like, okay, look, we know something about psi, right? We know that its null space corresponds to vectors that I can write as, right, so hold on, let's again, just write this down. Let's just say alpha 1, alpha 2. This equals 0 when alpha 2 hat is alpha 1. Right, so basically the second half of the vector is the negative of the Fourier transform of the first half of the vector. Right, so that's how we're going to argue that there's no other way to write f using a fewer number of terms. Okay, so let's just suppose that there were such a way. Right, and what we do is we'll say, suppose there was another beta such that phi beta equals phi alpha, and those two things weren't equal to one another. Right, what we're going to argue now is we're going to say, okay, if we have psi beta equals psi alpha equals f, then we must have beta minus alpha in the null space of psi. Right, and then we know a lot about the null space of psi. Right, we know that kind of the null space of psi contains all kind of vectors and their Fourier transform pairs, right? And then we know that the null space of psi, we know that there can't be a null space if these things are too sparse, right? If I'm asking both this Fourier, this time part and this Fourier transform to be both be sparse simultaneously. Okay, so that's kind of the tack we're going to take. Okay, so what does it mean if there's another sparse way to write f? Well, it means there's another beta such that beta doesn't equal alpha, such that, of course, I can rewrite f in psi, and that this, the number of terms in the time part of beta plus the number of terms in the frequency of beta is less than the square root of n. Right? This means beta is at least as sparse as alpha. Okay, so then what we say is now let's look at this is the difference between alpha and beta. So we just call h alpha minus beta, and then it must be that h is in the null space of psi. Right? If both psi times beta and psi times alpha equals f, then the difference of these two things, of course, has to be, when I apply psi to a minus b, it has to be equal to 0. Okay. So then, here comes the kind of key thing. What we'll basically say is, it's impossible for h to be in the null space because of the discrete uncertainty principle. And here's why. So if alpha has less than or equal to square root of n terms, right, and beta is sparser, say beta has less than square root of n terms, right, then if I subtract those two vectors from one another, h can't have more than 2 times the square root of n terms in it. Right, that's just if I take two sparse vectors and subtract one from the other, the size of the support can't be more than the sum of the sizes of those supports. Okay, so what this would say was, okay, look, if such a vector existed, it would have to have the property that h should be in the null space of psi and have fewer than 2 times square root of n non-zero terms. But this is expressly what this discrete uncertainty principle disallows. Right? You can't have this. Right? And let's just see exactly why not. So, if I have a vector h is in the null space, again, what this is saying here is like if the other sort of thing with h being in the null space is if I look at psi times h, right? And so then what this means is it means that the top half of h minus the basically the Fourier transform of the bottom half of h, that has to be equal to 0. Okay, so what this is saying is, so this says if h is in the null space, as we've argued before, it has the top half and the bottom half of the part corresponding to spikes, the part corresponding to the signs, those have to be Fourier transform pairs of one another within this minus sign. But if alpha and beta are both sparse, what this is saying is that h also has to have a small number of terms. Right? But we're seeing that if h has smaller than 2 times the square root of n terms in it, then those two conditions are compatible. Right? There's no way I can have H1 and H2 be Fourier transform pairs, and have the sum of their supports be bigger than 2 times the square root of n. All right, so what does that mean? It means alpha is the only way I can write f that uses square root of n of fewer times. Okay, so that exactly ties, this idea of sparseness decomposition back to this uncertainty principle. So, we have this sort. Let me back up here and say we have this kind of abstract result, or something result that just has to do with the time and frequency domains. And all it says is, any signal that I give you, if I look at the number of non-zero terms it has in time, the number of non-zero terms it has in frequency, those both can't be small at the same time. And by both can't be small at the same time, what that means is the product of their sizes has to be bigger than n. Or equivalently, the sum of their sizes has to be bigger than 2 times the square root of n. So what that does is it says, if I give you a signal that has a total number of spikes and signs in it that's less than the square root of n, there is no sparser way to write that signal. And so not only that, what it says is, okay, let's suppose, I observe an f, and there is some decomposition for f that uses square root of n or fewer times. Right? I can find this decomposition by solving this optimization program. I can look over all the sort of sets of expansion coefficients, or the weights on the spikes and signs that rebuild my signal f, and I can pick the one that gives me the fewer terms. Right? And if there exists a single decomposition that uses square root of n or fewer terms, that's the only one. Not only is that the sparsest one, it's going to be the only one that uses less than or equal to square root of n of terms. So it's necessarily, again, almost by construction, going to be the solution to this optimization program. Okay, so that's sort of how you tie, this idea of an uncertainty principle, that things are sparse in one part of the dictionary, can't be sparse in the other part of the dictionary. That's how you can directly relate it to the sparsest decomposition being unique. Okay, so, what I'll mention now to finish off this first segment of the lecture, but we'll talk extensively about on Thursday, is, not only does this idea of an uncertainty principle, does it have implications for just this, the sparsest decomposition being unique, but it also has implications on L1 being able to find that sparsest decomposition. So we'll see in a later lecture. So again, the first lecture that we'll do on Thursday is if we put just a slightly stronger condition on the sizes of t and omega. So it's been shown that if instead of the sum so if I can write f using a number of spikes plus a number of signs that's less than, say, 0.9 times the square root of n, I can recover that sparsest decomposition by solving this L1 optimization program. Right, so this is in kind of a paper from 2001 by Donahoe and his graduate student Xiaoming Ho. And again, what we'll do, so we'll prove something just slightly weaker than this result on Thursday. So we'll actually prove, again, almost through a direct application of the uncertainty principle, is that if this is less than 0.75 times square root of n, then L1 will find it. Right? So that basically means if a sparsest decomposition exists, you need square root of n. To find it using convex programming, using a basis pursuit, it just needs to be a little sparser. Right? So the best thing you know is 0.9 square root of n. We'll be able to easily prove 3/4 times the square root of n. Okay, so that's nice. So then, you basically go about it in almost exactly the same way. Right? So what did we do here? Basically, we said, okay, if we have a sparser decomposition, that means we must be able to move in the null space from this one decomposition to the other. And, and that said something, and being in the null space, this uncertainty principle, that just makes, it's just, a sparse vector being in the null space is just directly incompatible with this uncertainty principle. And that tells us something about this L0 problem. And so the argument for L1 is not that much different. I mean, you say if I have another vector that has smaller L1 norm, I must be able to move in the null space to that vector and simultaneously lower the L1 norm. right? Instead of lowering the sparsity, you're lowering the L1 norm. But again, what you do is you just use the uncertainty principle to show that such a thing is impossible. So that's kind of what we're going to do, and it's a slightly more general setting on our first lecture on Thursday. Okay, so that's good. So what you can also do is you can generalize this to just pairs of orthobases, path spikes, and sines. So actually, I think one of the homework problems asks you to recreate kind of some of the key points of the proof, but for just general pairs of orthobases. Okay, so like what we can say is like, a lot of what our argument hinged on was, again, this uncertainty principle between time and frequency. And that uncertainty principle existed because the time domain and frequency domains were so different from one another. And so, what you could say is, okay, if I have now, say I'm not interested necessarily in time and frequency, but I'm interested in just two fixed orthobases. Right? So obviously, if psi 1 and psi 2 are very closely related to one another, it would make sense that the sparse decomposition isn't unique. So if they're exactly the same, then of course the sparse decomposition is unique. Anything I can do with sparse in psi 1, I can do with sparse in psi 2, and any combination thereof. So what you do is you have this sort of measure, which is what we call the coherence, which measures the similarity between these two orthobases. Right? And all it is I just look at all the vectors and basis vectors in psi 1, all the basis vectors in psi 2, and I just look at the maximum of the inner product between these two. Right? So in the spike and sine case, right, these all just had one element in them, and these all had maximum value in this matrix is 1 over the square root of n. So if I took any column here and took the inner product with one of the columns here, I got 1 over the square root of n. So in this case, the coherence was equal to 1. Right? If these two orthobases share a vector, then one of these inner products is going to be equal to 1, and the coherence can be as bad as the square root of n. Right? So that's how you get kind of this upper and lower bound. Okay, so what you can say is exactly the same thing. So you can get an uncertainty principle that says if I have a dictionary formed by a pair of orthobases, psi 1 and psi 2, and those orthobases have some coherence, the first thing I can say is, there's no signal, there's no just vector in Rn, such that if I count the number of non-zero terms in the psi 1 domain, and multiply the number of non-zero terms in the psi 2 domain, that's lower bounded by n, but now divided by the coherence squared. Right? Or the sum of these two sizes is lower bounded by the 2 times square root of n, but divided by the coherence. Okay, so that's, I think this is what I ask you to prove on tonight's homework assignment. It's really not hard. It's really, you just go back through the steps here. And, where we used maximum size of elements in H, you basically just replace that argue that you can replace that with the coherence between these two things. But similarly, you can say that, if there's a way I can write F in this as a superposition of elements from psi 1 and elements from psi 2 that uses fewer than the square root of n now divided by mu terms, then that in some sense is the unique sparse decomposition. There's no way I can find a sparse decomposition, which means I can recover that sparse decomposition by solving this L0 problem. Right? And then it's also true, something that's just slightly weaker, which again we can prove very easily. That means, look, if I divide this condition by a half and add 1, then I can also do the recovery by L1. Okay, so that's this generalization of pairs of orthobases. So, what this sort of brings out, and what we'll kind of find interesting later, is it brings out this relationship of, when I can find a sparse decomposition, and here it relates it to what we call uncertainty principles. But really, what that was a relationship with was kind of the eigenvalues to submatrices of this dictionary. So really how we derive these uncertainty principles, we pulled out columns of the dictionary, and then we talked about, how close those eigenvalues had to be to 1 to be able to make this decomposition unique, right? And that's sort of a theme that comes up again and again in sparse recovery. Okay, so this is, again, these are all very special cases. You can generalize all of these results to general matrices, but also you can do something else. All right, so if we look back at our example of what kind of broke this spike sign uncertainty principle, right? So we said, okay, look, this uncertainty principle is tight in the sense that, I can find a signal that has, if I look at its, the size of the supported time, the size of the supported frequency, the sum of those two things just achieves this lower bound. But in some sense, this is kind of a very, very special case, right? In some sense, this uncertainty principle is delicate, and that this Dirac comb had to be very carefully constructed, right? And so, actually, what you could say is you could say something more generic. So you could say, okay, look, let's say, instead of asking for a worst case, let's try to ask for an average case. So let's say I pick a small number of spikes in time, right? And then, or just pick a small support in time, and say, to make it generic, say I pick that support in time at random. And then I ask, can there be a signal supported on that, small support which I've chosen at random? Can there be a signal that's supported on any small set in the frequency domain? Right? So it's kind of like a weaker version of this uncertainty principle. And the answer, for reasons that are far more complicated than what we've talked about today, happens to be no. Right? So actually, if we're sort of more interested in generic supports rather than all supports, we can say the following thing. So instead of t plus omega being less than the square root of n, if I select a t at random in the time domain, and you can either select the support in omega random, or you could say this works for all supports in the, or just keep a particular one fixed in the frequency domain. Actually, you can do much better than the square root of n. You can actually get n over the square root of log n, right, with a constant that looks something like an 8. Right, so as n gets big, square root of log n, it really starts to go away. Like you could bound square root log n by 10 and get a long way in life. So this is almost like a constant times n in some sense. So it's really moving from something that looks like square root of n to n. So all this is saying is like, well, of course, if you were interested in making an absolute statement about all supports in time and frequency, it has to be 2 times the square root of n. If you're interested in kind of the average generic case, or the typical case, it's really that the sum of the supports is like less than a constant times n. That's really, a more refined way of saying things. Okay, so establishing this is a lot more complicated than what we did, but it actually uses a lot of the same ideas. Right? Essentially, what it does, the proof of a statement like this, all it does is it just has a more careful treatment of this step right here. You just don't make this replacement of this step. Okay, so that's really all it's about. Okay, so let's end this first lecture here. How about we break for about 10 minutes? I'll see you guys back at 3:15. And then what we're going to do in the next segment is we're just going to give you a sort of an overview of this field of compressed sensing. Now we're starting to build up these ideas about sparse recovery. So let's we're just going to add a little more motivation over the last hour and a half. Okay, so I'll see you guys at 3:15 then, ish.